So hello again. Tonight we're going to talk about multimodal observing, and I'll explain what that is. So some people would say, why don't you just say what you mean? Make it simpler to understand. I think, well, sometimes you need a term or a phrase that is inclusive of what you're trying to say. And if I had said it in some other way, then it would not be as inclusive. So if you ever worked in the healthcare industry and you work with radiologists that do the x-rays and the CTs, the MRIs and the PET scans and such, those things are referred to as modalities because they're all making observations. But when you log the study, you have to say what kind of modality was used to gather this data. Was it x-ray, CT, MRI, PET? So it's common reference of modalities. The other interesting thing is when you talk about infrastructure projects in big cities and you want some depot center where you can transition from cars in parking lots to buses to maybe cargo carrying trucks to trains to maybe an airport, that's referred to as a multimodal hub because it's all transportation, but there's different kinds of transportation that interact with one another. So use of the term multimodal was not meant to confound people. It's just meant to be inclusive of what I'm trying to refer to. So had I used something more recognizable like electromagnetic spectrum or multi-frequency or multi-wavelength or multispectral, it would have been all referring to things that are of the electromagnetic spectrum or the EM spectrum. But I want to go beyond that. I want to go to other kinds of observing. So if you take into account radio, infrared light, ultraviolet, X-ray, and gamma, those are all electromagnetic spectrum based. But what about the things that you can measure that aren't EM based, like acoustics? You know, when some big explosion happens in outer space and it impinges upon our atmosphere, you can get very low frequency concussive waves that can get recorded from the Earth's surface. So acoustics are a thing. Vibration is a thing. What about magnetic fields? You know, when you start talking about energy outputs from pulsars and quasars, they can affect the magnetic field of the Earth, just like the solar wind can, solar flares can. So you need to be able to look in the magnetic field itself. Now, the magnetic field, we don't look at that directly. We look at that indirectly using the electromagnetic spectrum. So the magnetic field itself isn't EM, but how we measure it uses EM. The gravitational field, we actually have satellites in orbit that measure the variations in the gravitational field of the Earth. And they actually have a map. So you'll find like this thing called the Southern Atlantic Anomaly. It's a giant blob of difference of gravitational field on the Earth off of the central east coast of South America. And it affects things. For example, when the Hubble Space Telescope is orbiting the Earth, as it does about every 90 minutes, and it wants to do an observation that would carry it across the South Atlantic Anomaly, they actually shut down a lot of the electronics, close the front cover, go through the anomaly, and then open things back up and turn things back on. So when you see something like this observation was 30 days of accumulated observing, except for the parts every orbit where they shut it down to go over the South Atlantic Anomaly. So it's not 30 continuous days. It's slices that are added together. And then we all know now that there's this thing called the gravitational wave background. When they first did the studies, they didn't think there was a background. It was just, well, when neutron stars collide or when black holes are formed, you get gravity waves. Oh, no, there's gravity waves all the time. It's just they're very low amplitude, very long, multi-light year almost wavelengths, and we didn't have the instruments to pick it up. But when they started using the pulsar timing array, which will give you variations over many light years, they detected the cosmic gravitational wave background. So now you know why I'm using the term multimodal. Is in astrophysics and astronomy, we want to take it all in. In fact, we want to do it in a coordinated manner, like, hey, I just detected this in gamma. Are any of you guys in the other modes seeing something? And we find new science when that occurs. The first one I recognized was when a star goes supernova, you don't see the light first. You don't see the gravity waves first. The first thing you see is a stream of neutrinos. But neutrinos can't travel faster than light. Yeah, I get that. But they can travel right through nebular dust and debris and planets, and they can travel right through that. So while they're not faster than light, they're just the first thing to arrive because nothing stopped them. So sometimes observing what isn't easy to observe is the right way to go. So I broke down multimodal. I said, well, there's the EM stuff. There's acoustic. There's two kinds of acoustic. There's non-contact and contact. If you're talking about non-contact acoustic oscillations, most people would just go, oh, sound. Well, sound is sonic because of our human physiology, but you can actually have sound waves that are lower frequency than we can hear. Those are infrasonic, or sound waves that are higher in frequency than we can hear. Those are called, oh, look, an extra comma, ultrasonic. Well, when you have things in contact, you can not only transfer acoustic oscillations, you can transfer vibrational oscillations. And to pick that up, you need accelerometers, and you need them in multiple dimensions because not only can they butt together, they can also slide around one another. So you need to be able to measure the acceleration forces in multiple dimensions. And then we know about gravitational fields of planets and how they interact, and how if you measure the gravitational field of the Earth versus the gravitational field of the Moon, the center of gravity between the two objects is actually just below the surface of the Earth, not in the core of the Earth. And it's even more bizarre when you talk about dwarf planet Pluto and Charon, which is its largest moon. The gravitational center is actually above the surface of Pluto and between Pluto and Charon. So gravitational forces are a thing to be measured. And then, of course, gravitational waves. And we're now realizing that we need very much longer wavelength and lower amplitude to be able to detect those. So we start using the pulsar timing array of NanoGrav, not just LIGO and its European equivalent. Those are the giant, multi-kilometer long L-shaped things. Then we also have direct versus indirect sampling. So light, for example, if we're measuring light, we can directly get the photons to convert to electrons and measure the electrons as a charge, and it's a direct sampling. There are some things that we have no ability, we have no sensors to do direct sampling, like neutrinos. So what do? Well, neutrinos will rarely interact with other materials, and they'll produce this weirdly blue light for a moment. And so we detect neutrinos not directly, but indirectly by way of something called Cherenkov secondary emissions, or Cherenkov radiation. So there are observatories for observing neutrinos that have never observed a neutrino and will never observe a neutrino. They observe Cherenkov radiation, which is as a result of a probability of neutrinos interacting with things. But this term of spectral, spectrum, and spectrographic, that's literally just referring to if I have a set of data samples, and those data samples have an amplitude over time, that's a wave. If I analyze that wave, regardless of whether it's electromagnetic spectrum or acoustics or gravity or any of these sorts of things, they'll all have an analog counterpart, a wave, And if I do things with the wave to say, I'm getting this frequency, or I'm getting this amplitude, or I use a fast Fourier transform and say, it's affecting this wavelength. Those are all referred to as spectrographic analysis. So we can do it with radio waves, acoustics, contact vibrational, gravitational waves. All of these things can have spectral analysis. So if we're observing at different modalities, meaning different instruments, different ways of observing at different times, we need to know when it occurred. So if I get a gamma ray burst off in that direction at this particular time, and then I say, hey, let me put in a call to my ultraviolet friendly space telescope or my X-ray friendly space telescope, what are you guys seeing? Well, when did you see what you saw? And we'll go back and look at our records and see if we saw it too. Well, you need to know what time it was. So whenever you gather data, it has to be time-stamped down to a very fine level precisely. So you use atomic clocks, you use water particle fountain clocks, you use very, very accurate time of day sources. The one that I use is a small stratum or a stratum 1, not quite a stratum 0, but a stratum 1. I use a GPS receiver that has what is known as a pulse per second detector in it, and I bring that directly into the kernel level interrupt of my microprocessor running Linux, and I can keep the time of day of the Linux computer aligned to less than a microsecond, which when I timestamp things, I know it's exactly there. And I always base it on coordinated universal time or UTC time. That way, no matter where somebody references it from elsewhere on the planet, the data can be aligned. The data can be, post-processed and say, well, we saw it in this mode here at the same time we saw it in that mode there, or they were slightly separated by an hour. And then you have to go judge, how come it got delayed? Or how come the other one came in early?
Do you have your own GPS, or you derive it from GPS signals, or you have your own GPS clock?
I have a GPS receiver, and it receives and breaks apart not just GPS, because that's US only. The global way of identifying global navigation system stuff is GNSS, and my receiver is actually GNSS capable, so it doesn't matter whether it's a US GPS satellite or a British satellite or a Chinese satellite or a Russian satellite. If they're producing these signals, I can detect them, decompose them, and I can get a pulse per second that is accurate to 10 nanoseconds or 10 billionths of a second. And then I take that signal and I direct it in to the processor as a kernel level non-maskable interrupt. So when it interrupts the processor once a second, it interrupts it very precisely at 1 second. And then the amount of time it takes me to realign the 1 second mark of the microprocessor is roughly about 3 to 5 nanoseconds to get the signal lined up again. So I can very easily, over long periods of time, say my time of day and all my timestamps of my data are accurate to within less than a microsecond. I can't say it's accurate to 100 nanoseconds because I'm using Linux, which is not a real-time operating system. And once every 5 minutes, it goes out of sync for 1 10 nanosecond aligned pulse, and then it goes back in. So if I was running a real-time operating system, I could easily say I'm aligned within, 15 nanoseconds.
Is this connected to your radio telescope so you can time when you get a signal? No, yes?
Yes, it's connected.
Oh my God!
It's connected
this is
to my,
just like a radio antenna. Oh my! So you can time those events.
It's like
Jesus
Christ. It's like a real professional radio observatory. Just my little humble thing at home. But I don't do things like helium cool it or anything like that. I let all that stuff take place up in the GPS satellites and on the ground-based atomic clocks. All I do is when that 1 second pulse comes by, and I know it's aligned within 10 nanoseconds, I will align the 1 second mark of my Linux microprocessor computer to that signal. And there's a little propagation lag of about 5 nanoseconds. So I'm not to within 10 nanoseconds, more like 15 nanoseconds. But then every 5 minutes, it goes out of whack by, a large number of nanoseconds that I pull back into alignment. And so I can say, I'm closer to a microsecond or two. But you can do that, and it's not expensive. And it doesn't cost you, hundreds of dollars for a rubidium atomic clock synchronized receiver.
Yeah. But writing kernel interrupts probably isn't something everybody can do.
That's where Linux comes into play, because when you get the NTP software, the Network Time Protocol software, and you add that module to your Linux system, you can select, do I want the PPS, the pulse per second fudging? And it's just something you can figure in. You don't even have to write the software. You just go, yes, I have a receiver that can receive GPS and has a little parallel pin coming out that I can direct into an interrupt on my Raspberry Pi, and it will give me a time of day source that's accurate to much more than any over the internet. Because over the internet you can get accurate to 60 milliseconds or so, which is pretty good, but you can do better these days.
Hats off.
But if anybody gets really interested in getting their clock as aligned as cheaply technically possible, remember, I operate in the dirt cheap realm of things, so I have a solution.
Yeah, I use one of these things, which is off by about 4 minutes.
Yes. A 32 kilohertz crystal oscillator is good for about 1 minute per month. I have WWV synchronized clocks that are good for about 1 second per month. So someday I'm going to build a big enough display that these old eyes can see it from a distance, and it will have like a little Raspberry Pi 0W and a dedicated GNS receiver and a little stub antenna, and it will give me the time of day out to several digits, constantly flipping. So I found this fascinating, that there is so much data coming in from all these various modalities of high accuracy these days that the daily collection of data for ALMA, that's the microwave radio telescope array, high in a mountain in South America, they take in petabytes, that's 10 to the 15th bytes per day of data. There's no human being that's looking at all that data. They have computers looking at the data as it comes in, because, okay, so let's say I have an array of mass storage for my computer network that can store 5 petabytes. Great, what do you do on the 6th day? You got to start throwing stuff away. So you need something in real time at the front end that is actually sifting through all the data, looking for things that you're looking for, and looking for the oddities that you don't expect and need to detect. So there are 2 computer algorithms that are all the hot stuff in the news. One is machine learning, and the other one's artificial intelligence. And machine learning is you train the software to spot things. So if you're looking for, let's say, the next red dwarf or brown dwarf, you can have an algorithm that will look over petabytes worth of data per day and find all the brown dwarfs and red dwarfs your heart content in large surveys. So when GAIA is pulling out lots of data, or when ALMA is pulling out lots of data, and you're looking for known specific things, you can have machine learning algorithms that will go find them for you. Now, they won't give you a heads up immediately because they find too many of them. In a galaxy that has over 100 billion stars in it, they might be finding thousands of these things per day. So log it. We'll get back to you on that. But all they do is they just report out and go, today was a good day. We found 150 new brown dwarfs. Okay. Hey, undergraduate cheap to keep team. Go start looking through these things. And the other one is artificial intelligence. And the way I describe that is one of these things is not like the others. So you train the algorithm to, if you look at the Messier catalog, the reason why he came up with why Charles came up with the Messier catalog so long ago is he was looking for comets, and he didn't want to be disturbed by all these clusters and galaxies and nebulas that weren't interesting to him. So he cataloged them all. So AI is doing the same sort of thing. They're taking all the stuff that you know and love and going, ignore that, ignore that, ignore that. And the machine learning stuff is going, log that, log that, log that. And the AI can take the things that aren't one of the usual suspects and go, that one's different, and log that. So you have the things you're looking for and the things you didn't know were there. And so you use machine learning and AI to go find this stuff. So there are things that go bump in the night, as the saying goes, that are unobservable in the real world. And so I picked up a couple of things that, should I actually go to the effort and record them, you might know what they are. You can get these elliptical, very magnetic, egg-shaped things. They're affectionately referred to as rattlesnake eggs. And you pull them apart, and then if you just sort of grab two of them together in your hands, they'll go, and then they'll stop. But that's all you can hear. Then the thing where you grab the ball and it swings and hits the other balls, and the one on the end bounces back and it goes clackety, 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 clackety for an annoyingly long period of time. It turns out that when you think you started hearing it and when you think it no longer made any sound, there are actually more data points you can suss out on the ends of that than are possible with human physiology. So the rattlesnake eggs start rattling before you hear it. Not, loud enough, but actually subsonic frequency. So they'll do that as they start, and they'll do that at the end, and you just think, So they rattled for 3/4 of a second. No, they might have rattled for a second and a half. You only heard 3/4 of a second. Same thing's true of a Newton's cradle. When you get that first one to hit, the balls in the middle start rattling before the ball on the end starts swinging out. And when it comes back, the same sort of thing. So when you think it's done, it's still rattling. You just can't perceive it visually or audibly. The same holds true for gravitational waves. So here we have from LIGO a spectrograph. Actually, it's not a spectrograph, it's a waveform analytical. It shows you the strain, or how high the amplitude is of the gravity wave. And then across the bottom, you see time. And you can see it gets out to 0.05 seconds, a very small amount of time. But if you look at the waveform, it starts longer, goes to higher amplitude, tighter frequency, and then it trails off. But if you look at the left end and the right end of that waveform, there's more data there. It's not at zero, it's at, whatever they want to call zero. Well, as it turns out, when you start looking at things using the pulsar timing array, it goes at a lot longer. But, because LIGO can't detect that, it's not included in the scientific results. But as we have new instruments and we start looking out further to the edges, there's data out there. If you remember the movie Contact, when they first started hearing the high amplitude sounds coming from Vega, they said, wait a minute, I can hear there's more data here. And they started looking at it in different frequencies, and oh, look, there's TV signals. Oh, look, there's audio with the TV. And it's all because you start looking beyond the easy stuff. But let's say we have stuff that's beyond human physiology ability to detect and perceive. You can record it, But how do you let people know about it? Well, you have to remap it. You might take an analog waveform, and if you notice the gravitational wave, it's, not even a full second. Yet, when LIGO wanted the general public to hear a gravity wave, they took that signal, remapped it to something that's audible with human hearing, that's changing the frequency, and then they spread it out and raised the volume. So now it's, like 3 seconds worth. And you hear it rattle to a high frequency and then zip, go away. That's not how it actually sounds. You couldn't hear how it sounds. But by remapping it, people can get a cognitive connection to, oh, that's what it does. Same thing in imagery. If you look at a picture taken by a gamma ray telescope, there's nothing visual there, or X-ray, or even deep UV or deep infrared. There's nothing the human physiology can detect there. So what you do is add additional colors. Well, we're not going to come up with new colors. We're just going to take the colors that it might have been, like, let's say, pinks and reds. And whatever was in visual pinks and reds, we'll make those greens and blues. And then we'll take the stuff that was in deep infrared and make it pinks and reds. So we're doing remapping, we're doing substitution. So in a single picture, we can show you gamma, X-ray, UV, infrared, and even radio with a single picture. But if you were able to look out into space, you wouldn't see even a fraction of that, because our human physiology is just incapable of detecting it. But that doesn't mean it's not there. Here's another thing we do: signal domain transformation. This is where the Fourier series and the fast Fourier transforms come into play. You can have a gravity wave, and you can see the little analog signal pattern. But if you sort of, as Zane goes, rotate that on its head, and instead of seeing amplitude as frequency over time, you rotate that around, and you have the frequency going across, and you have time scrolling down, and then you have specific frequency within a band, and then the amplitude of it changing the brightness and width of the signal. So if you're looking at a computer modulated data signal, it's going to be very narrow and almost continuous. So that straight bright line left of center, I can tell that's computer data modulation. But the stuff over on the right that is all choppy and wide and narrow, that's a person speaking, because our voice goes through frequency ranges, and our voice goes through different volume amplitudes. So you can look at a waterfall like this, or a waterfall plot, and see that's computer data, that's somebody speaking, just by looking at it.
Yeah, Monroe. Well, that's obvious to all of us, but nonetheless, that was a joke. Nonetheless, maybe in some other talk one night, you could show us voice in the normal domain that we look at it, as opposed to being in the waterfall domain, and also radio as opposed to the waterfall, because it's not obvious to me how one of those is, how that's speech. You know how you normally see speech, right? Oscillating with volume
You'll see
and
speech like on the
frequency.
left. The speech will look like it is on the left. It'll be an amplitude frequency waveform. Yeah.
And how exactly is that mapping to the FFT waterfall?
So the picture on the left is the height of the waves over time. The compression of the wave peaks and valleys is frequency. So you have amplitude, frequency over time.
Right.
If you use
what's
a Fourier
the one on the right, the waterfall? How does that relate to this?
Okay. If you use a Fourier transform, you can take your amplitude, frequency over time, and you can rotate it and make time data points moving. So this display is not static. It's actually raining down. That's why they call it a waterfall, because it moves down the display in real time. And then as a particular frequency is modulated, the frequency is widening and narrowing. So the line that is straight has a very, very narrow frequency range or a spectrum. The stuff over on the right is the frequency range of human speech, which is fairly wide. So the frequency of modulation for that is narrow, wide. You can tell there's like a tone in the background, then somebody speaking. And so you see frequency going out horizontally, and the amplitude is brightness. And then time is just the signal changing over time. But that is a good point. I think it would make sense for me to do a Saturday evening session to show signals analysis, to show.
Yes, yes. I thought Fourier transforms just broke stuff down, broke complex signals down into their composite sine waves.
And that's actually what's happening. That's a Fourier series. You can have.
That's what's happening? I don't understand it.
Okay. You can have sine, cosine, or just sine or just cosine. And depending upon the particular factors you're using and how many terms you have in the series, you can take all the data points and say, well, after I've done 3 factors, that's good enough to put a point on a graphical display. I don't need like 27 factors because I'm not going to be zooming it up that far. So you're taking all the data points from the signal on the left, and you're doing a Fourier series transform, a power series, to say every data point can now be calculated as how bright do I make the point as the data moves down and changes.
Monroe?
Yes.
It appears to me that you're going further down and losing me more than trying to. So I think like what he's saying is having a whole program on it by itself would probably be very good, because right now it's like you're too far into it. So if you start at the basic, it would be very good to start at the basic and then to get to here.
Yes, and I agree. And we will do a separate discussion, and I will show you real-time waveform analysis of radio signals. Both
I look forward to it.
As a spectrum and as a waterfall.
Okay, thank you.
Okay.
Yeah, and maybe you should show how a Fourier transform and a fast Fourier transform work, mapping those together to analyze that data, maybe.
Oh, now you want to see math.
Oh, that's gonna be hard.
That takes a long time.
Yeah. Most people don't like seeing math.
Okay, I can just research that. I can just research that on the internet.
You can show the math, Monroe, because you do talk about it, even if you don't show it.
Yes, I can have a 1-slide basics of Fourier series and Fourier transform.
Oh, there's about 10 YouTube videos on it.
Yes, there are. And in fact, at the end of this presentation, there's hyperlinks that will tell you how to find what a Fourier series and a fast Fourier transform are, and what a waterfall is. And so.
And you're going to say which one's the simplest, right? To understand.
None of them are drop dead simple, unfortunately.
That's what I figured.
I can tell you why you would want the data on the left and the data on the right. I think they're both important because they show different things about your data.
But if you do this presentation, it would give us a direction and give us the basics so we would understand better these videos, right?
Yes.
Okay, then I look forward to your presentation. Then I'll go look at the video.
It'll probably be early in the next year.
That'll be fine.
Okay.
It was a good idea that he had.
Thank you.
I don't know who that was. Who was it that had it?
Adam.
Thank you, Adam.
So everything that we measure digitally is as a result of something Einstein came up with in the early 1900 noughts called the photoelectric effect. If you take a photon and you run it into a material, your sensor material, and it has a certain amount of metallicity or metal in it, then it will produce electrons out or a voltage. And if you measure that voltage using an analog to digital converter, you can have a digital value for whatever the signal is. And depending upon the materials of your detector, there will be things that your detector can pick up and things that your detector is unable to pick up. So you have to have different sensor chemistry based upon Am I a gamma ray telescope, or am I visible light, or am I infrared, or am I radio? So different detector materials pick up different ranges. And a lot of these signals, these electron charges, are extremely low. They're in nanoamperes, or billionths of an ampere, or billionths of a volt. So you have to run it through cascades of amplifiers called low noise amplifiers in order to get the signal boosted up high enough where you can now do your analog to digital conversion and get, a range of 5 volts. So there's a lot of pre-processing you have to do. And if you ever really get into that, you can look at the Large Hadron Collider over in Europe, and you can see the billionths of an ampere that they will use photomultiplier tubes to boost up to a tolerable signal range of 0 to 1 volt. But they measure it at a very fine degree, so they can measure it in, not just tenths of a volt, but maybe millionths of a volt in that 0 to 1 range. And then it's, okay, we're sampling the data. We get a digital value out. How often do we sample it? Because there's this guy named Nyquist that said, if you want to measure something that changes 10 times a second, you need to actually sample it 20 times a second, because that way you see all the edges of the curves, because your sampling may not be in full alignment with the wave change. So your sampling rate and how many bits per sample, and whether you get the full range where it's pluses and minuses, all that affects your data as to how good is my data? What's the quality of my data? And then, okay, now I want to transfer that over an interface. Let's say, I don't know, USB, Ethernet, or whatever. It only goes so fast. Me sampling something a billion times a second and then running it over USB that can at most transfer 240 megabytes per second is kind of pointless. So all of these things are balanced as to how much you can take in, how much you can get out. And then it's, well, what kind of interface do you have? Is it serial? Is it parallel? How many bits of overhead per sample? All that stuff. And then somebody says, oh, I'm transmitting it over Wi-Fi. Well, is that encrypted? Because that's going to add extra administrative overhead to every block of data that you send to encrypt it and decrypt it. So all of these things have to come into account when you say, I've got a radio telescope array and it's collecting data, and I'm doing petabytes of data per day. Are you? Or is that just how much you're actually capable of collecting? There may be tens of petabytes of raw data that are coming from your sensors, but you can only chuck it in and store it so fast. Now, this is where the devil gets into the details. If you were ever able to actually look at the raw observational data from some of these science programs, you might realize that they're not trying to pull the wool over anybody's eyes. It's just the technologically minded people know the ins and outs of their sampling, and the general public just sees the conclusion and doesn't know, oh, it's not that they scrimped on it or ignored it. They just, they know what's going on, and their peer group knows what's going on. So if somebody says, we used the James Webb Space Telescope and we looked at that particular galaxy and we came away with the following spectral analysis, and we concluded that the following, like there be sulfur in that spectrum. Okay, what is the scale of the data? How much sensitivity did you have to detect that little tiny narrow line that said sulfur? Because it's a particular wavelength. Did you accurately get that? Well, I'll have my peer team review it. Okay, if they look over your data, they can go, looks like you used it properly, but what about the instrument? What about the telescope? Well, let's do a peer observation. So a different team will use the same instrument, looking at the same target, and get the same data. Amazing that, because they're using the same instruments in the same place in deep space. So when they get the same data, it may be no surprise. So when somebody says, I know that's your observation, but let's wait until it's peer reviewed by a different team using the same deep space instrument. Odds are they're going to see the same thing. Look, it's been confirmed. Not really. It's been identified that you didn't do anything knowingly wrong in your procedures for collecting and handling the data. But as to whether that particular instrument's got a flaw or that particular instrument's not as sensitive as you think it is, that's a different story. And until you start digging, you won't find out. I'm looking at the James Webb Space Telescope going, okay, they can see in maybe a little bit of orange, definitely red, darker red, near infrared, mid-infrared, but not far or deep infrared. That's the sensor range. So how can it conclude that there's something in the spectral analysis at the ultraviolet end? They're looking at the chemistry going, well, if we've detected this in the infrared range on Earth, that chemistry typically has also a spike in the ultraviolet range. So that must be there too. But you didn't actually observe that. You're just presuming that because of how things work on Earth and because we detected it out in space, that it should be there. But you have no evidence that it is there. So it's good to look with different modalities, even if it's just different modalities in the electromagnetic spectrum. Because once you do that, you may find discrepancies. And, it's when your peers prove you wrong. But for all these other modalities, we have even fancier, modern, contemporary technology, quantum level technology that we measure that stuff using. And it's still analog to digital converters, and it's still measuring voltage in fields and things like that. But these are sensors that are down to, millions of a meter in size. They're called Micro-Electro-Mechanical systems. Now they're called mechanical, but they're not like, they don't have moving dials and gears. And think of it as tuning forks. If I can have a piece of quartz crystal that when you bump it, the free tongue that's hanging out microscopically in space moves up and down. It's quartz moving up and down. And that says piezoelectric voltage. So if I can have my low noise amplifier measuring the voltage produced by my piezoelectric tuning fork, and I have 3 of those in different axes, I can measure the force in X, Y, and Z directions. So that's how you have accelerometers and gyroscopes with no moving parts. And you can even extend that out into magnetometers for measuring magnetic and gravitational fields. How about this one? The least expensive, most sensitive microphones are piezoelectric microphones. They just have a little tiny quartz disc, and then as the sound wave smacks into it, they pick up the voltage off of it and then amplify the hell out of it and go, here's your sound. So as we start using more and more MEMS chips and products, you might be unaware that your mobile phone that says, hey, I'm at this location and we just turned left. How do you know it just turned left? The accelerometers in your phone that make use of MEMS chips said, you just swerved that way at, 0.25 Gs. Or I dropped my phone. Your phone knows it got dropped because it fell. It accelerated through the gravitational force of the Earth, and then all of a sudden it came to an immediate stop. It knows it fell. And what's even weirder is your phone knows when it hit the ground if it was in your pocket or not. Because your body dampens the oscillation of the impact. So if you happen to be, let's say, a nurse in a hospital and you're walking down the hallway and you've got the right software running on your phone and you trip and you fall in the hallway and do a face plant and you knock yourself unconscious, I know software that can actually detect that and go, nurse down. Here's the last known location. So these things are in practical use in the world around us, but simply because it's not in our daily bailiwick, I don't need to know that stuff. Just make it work. It does. It works. It's in your phone. Oh, one thing I left out here, which is the very last one. People recognize that GNSS or GPS are good for giving you your latitude, longitude, and altitude. Guess what? They're not that great at altitude. Because as the satellites are orbiting the Earth, they're bouncing up and down in the gravitational anomalies of the Earth. So if you're expecting the radio telemetry and the measured distance and timing to give you an accurate measurement of altitude, guess again. However, if you happen to have an ambient pressure sensor, which is another type of a MEMS chip, it's measuring the force of the atmosphere and producing a piezoelectric effect. It can more precisely tell you your altitude than can GPS. So whenever I'm measuring, like, where did you plop your telescope down? Latitude, longitude, GNSS, altitude. No, acoustic, barometric pressure.
Well, shoot, Monroe.
Yes.
When you're not busy, why don't you use some 3D printing to create an ion trap quantum computer and just use MEMS chips to cancel out the noise when it's swinging to the left or swinging to the right or the pressure's going up or down. That should be an interesting project.
As the saying goes, that's too much like work. Yeah, that would take me down an enormous set of rabbit holes to get that all right. I've done it on the telescope mount that I worked on because I wanted all my astrometric calculations to take advantage of latitude, longitude, elevation or altitude, and where the telescope was pointing. So I needed the MEMS chips to tell me, what is the pointing direction of the telescope, where I'm located, how high above sea level I am. So I took all that into account. And strangely enough, the astrometric algorithms that are already out there freely available, they actually had places where you could put those parameters. That was very reassuring, which says this is professional grade stuff. But anyway, yeah.
Have you seen the YouTube videos or other stuff where you can relatively easily build an ion trap at home using lycopodium powder and subjecting it to a circular field and just, in fact, it's an AC field that they're using. So it appears to be standing still, but if you slow it down, it's moving back and forth, but doesn't get to the end of the field. And as you vary the voltage, I think, then you start with like a little bit of lycopodium powder, and then it starts to split up until you wind up with just one. The lycopodium powder, I think, is pollen from a moss or something, and you wind up with just the single one. So you there. I've already told you how to do the ion trap. You just need to, filter out the noise. You've seen those, yes? No?
Not as an ion trap, but as a means of moving particles. It's a levitation. I've seen it done acoustically. I've seen it done electronically, and you can hold things in fields pretty solidly.
Right. So if it's electronically, it's the way they're doing it with this powder is electronically because it ionizes to be positive. The lycopodium powder is the stuff where you sprinkle it on top of water. It's very hydrophobic. So you put your finger in or something like that, and your finger doesn't get wet. It just gets the powder on it, and you pull it out. Stuff like that. So it's becoming it's positively charged. So it's already an ion. Okay. You don't have to really do that, but I mean, the MEMS chip that you're MEMS chip you're talking about makes it sound like it's theoretically possible.
Yes, it should be theoretically possible. But the one thing that I did see this week that I thought, well, that's going to change a lot of people's opinions. Sabine Hossenfelder, Science Without the Gobbledygook on YouTube, was describing a linear accelerator that was 6 inches long. And the particular technique that they were using was accelerating particles and then adding in a laser to trap the electrons. And wait a minute, I thought when you shine a beam of light into another beam of light, the photons don't interact. Well, apparently they do at the quantum level. So the photons were corralling the electrons to accelerate them further. So they were getting up to 1 giga electron volt or 1 billion electron volts in something that was 6 inches long. So yes, there's a lot of science. There's a lot of observational modalities that we're coming to grips with that can be very valuable. And once anybody can do it, it's kind of like when only big observatories could observe comets, only big observatories could find comets. Well, now that every backyard enthusiast has himself a digital camera and a telescope, a lot more people can see comets. So we're finding a lot more comets. Same thing is true as modalities get smaller, cheaper, easier to use, and software is plentiful and available. You're going to have amateurs bordering on novices discovering things, and the professionals have to catch up. So let's say, how do I measure things? Well, in the electromagnetic spectrum, for a single point data source, you would use a diode or a transistor or a radio receiver. If you have a matrix of sample points, most people think of that as a optical plane or camera back. So you can have those, but if you want to make it even bigger, you can have synthetic aperture or interferometry, and with a bunch of individual receivers spread over a large area, you can synthetically make something very large, like an Earth diameter radio telescope. The way you do it in light is you have to have different sensor materials and different filters so you don't get a lot of noise. And then whether it's infrared, which you know the James Webb Space Telescope has gold-plated beryllium mirrors, because the beryllium can be hard, doesn't expand and contract too much, and you put gold plating on there, which reflects infrared light, but lets other forms of radiation pass through. So depending upon what wavelengths you want to pick up in the EM, you might use different materials for different bands. When it gets up into high energy, let's say gamma, you can't really focus. X-rays you can focus with an electromagnetic field. Gamma you can't. Gamma just comes in, and what you do is you cleave off using thick osmium heavy density plates. You cleave off the parts of the received gamma that you don't want, and now you have a focused gamma beam. Different means of reflecting and focusing based upon the wavelengths.
But Monroe,
yes,
when you're saying this, sometimes I'm taking it like there are people that are amateurs that can do this, and but then other times I'm not sure when you're saying an amateur or if it's just happening out in space that they can do this.
If it's X-ray or gamma or high energy UV, that can only be done from space.
Okay.
If it's infrared in the near infrared, or obviously if it's visible, any amateur on the ground can do that. If it's radio, as long as the radio frequency penetrates the Earth's atmosphere, then amateur radio astronomers can do it. And I belong to an organization called SARA, Society of Amateur Radio Astronomers. And you've got people, much like people will have a backyard telescope, there are people that have 10-foot diameter, 3-meter parabolic dish antennas that are steerable in their backyard.
Now, are these are more expensive than like telescopes, right?
I would say a 12-inch telescope optically with a good camera in the back is more expensive than a 10-foot radio telescope.
Okay. Now, when you were talking about these plates are out in outer space, though, right?
Correct. That's okay. For how do you focus something that you can't focus with electricity? light you can focus with lenses and mirrors. How do you focus X-rays? Well, you use magnetic fields. You have magnets. Well, how do you focus gamma rays? You can't. All you can do is say, the stuff that's not going straight, block it. So you have a series of blocks that are made out of very dense materials that are slowing down the gamma so they don't get detected. But yeah, you can only do that in space.
And you don't want the gamma detected because why?
There's a lot of gamma in space. And if you want to point your gamma telescope at a particular spot in space, and you've got all this gamma coming in, you want to narrow it. You want to get your gamma beam collimated. So you only want the gamma coming from that direction. So you put the plates in place, and so all the gamma coming in from the other directions gets taken out by the plates, and only the gamma coming from that direction is what you record.
And what is gamma looking for?
High energy physics in things like exploding stars, black holes, stuff like that, quasars.
Excellent. Thank you.
Okay. So in radio, we talked about software-defined radio that $20, anybody can get involved. But at the high end, for the professional stuff, you have purpose-built radio receivers that only receive in a certain range of frequencies, and they amplify considerably. And the receivers and the amplifiers are all cooled in liquid nitrogen or liquid helium and liquid nitrogen. So they're super sensitive. So amateurs won't do that. But if you're receiving things like pulsars, radio signals from other space probes and such, a lot of amateurs can do that in their backyard. If you want to measure your rattlesnake eggs or your Newton's cradle, yeah, you can buy yourself a piezoelectric microphone, a MEMS microphone, and measure that. Or you can go buy the circuit boards and measure accelerometer, gyroscopes, and magnetometers, and you can measure the very, very tiny movements of things. When it comes to gravity waves, there are folks over in the UK that are working on desktop gravity wave detectors. And the way we measure gravity waves is we don't measure them directly. We don't measure the mythical graviton particles. Someday they'll find them. But we don't measure graviton particles. What we measure is stresses on the fabric of space-time. So if you have two very sturdy things that are separated and at the nanoscale, they suddenly wiggle closer together imperceptibly to the human eye. That's a gravity wave. So as they make sensors that are more and more sensitive to lower amplitudes, longer wavelengths, higher frequencies, higher sample rates, you can start to measure gravity waves with things that aren't, a giant L 4 kilometers by 4 kilometers. You can measure it on something on a desktop. And that's what the folks in the UK are trying to do. Is there's a research team that they want to make a desktop gravity wave detector. More power to them, because then any amateur can do it. Any knucklehead can measure gravity waves. So as we have more modalities looking at the same thing happening at roughly the same time, we can start to go, oh, when that happens in gamma, we can also see at roughly the same time the following things happening in X, UV, visible, infrared, and radio, like gravitational lensing, or things that move through things like neutrinos. We can measure all of these things more precisely and understand them more fully as we look at them with different modalities. And if you look at the history of neutrinos, neutrinos were originally claimed to have no mass. They were massless, like photons. And then as they started to figure out that there are different flavors of neutrinos, energy equates to momentum, momentum equates to mass. Look, neutrinos suddenly have mass. Just ignore the man behind the curtain who said they never had mass. That was then, this is now. Ignore that. Well, we are currently saying that photons have no mass. But photons have an upper speed limit of the speed of light, or c. Well, we found this thing called the Higgs field. And it seems to be everywhere. And if photons go places through space-time, and they're all encountering the Higgs field, maybe, just postulating here, and I've done this before in presentation, maybe the Higgs field is a universal slowdown of photons so that no photon goes faster than the speed of light. Why is C? Well, there's actually an algorithm that allows you to discern the value of C without actually measuring something moving at the speed of light. And it's a consequence of waveforms. You know, you divide these two things out and look, you get C out to a very fine precision without actually having to measure like light. It's physics. So in conclusion, observational programs are coming to realize that event effects in nature occur across a broad range of modalities, and that many observatories, not all, do try to work jointly across modalities. So if you get let's say, an X-ray detection, they'll talk to the gamma ray folks and go, did you see it? We saw it. When did you see it? Here, where, there. Okay. But they might not talk to the infrared folks, because that's the infrared folks. That's a hopeless mess. There should be a central wire system for communications of discoveries, not peer-reviewed, not concluded science, but just, hey, we saw this. They should have that between all the observatory operations team, not the science teams, not the principal scientists, but just the operations team, so they keep a log of them.
Like a hotline.
Yes, there should be a hotline between all observatories, and there should be a single channel that's available to amateurs. That actually exists for minor bodies in the solar system. There is an email address that you can send an email of a specific form into the Minor Planet Center, and they will say, okay, you're a person of known capability, known experience, known rationality, and you say you've seen this here, and you saw it move in that direction over this amount of time. Good, we'll log that as the first observational event. And now we'll get the professionals involved, and they will follow up. And if they follow up, you might get an asteroid named after you because you were the first to see it. As more modalities trickle down into the amateur community, they may be seeing things that the professionals have to go learn about later. You've got to know how this stuff works. As the saying goes, you got to know how things work on a starship in order to understand what modalities are good for what modalities are reasonable for an amateur to be able to use, and then how you process the data, learning what fast Fourier transforms and domain flips of frequency and time do. So I updated my About page. I now have hyperlinks to a lot of the stuff that I made reference to in all the organizations that I belong to. And then we have lots of links. So people go, what are rattlesnake eggs? It was very funny. When we were at the GEM show in Miami, there was a booth where the guy was selling resin sculptures, because it's a nature kind of show. He had a rattlesnake coiled up, and then he had rattlesnake eggs at the base of it. But he was also selling hematite rattlesnake eggs. And up until Helen and I showed up, he had never made the connection. They're both called rattlesnake eggs. Why is that? Well, if you look at a rattlesnake egg, it's a little bit puffier, but it's white and it's elliptical. It's not round. So rattlesnake eggs, and they rattle like rattlesnakes. So rattlesnake eggs.
How do you get eggs out of a rattlesnake? Very carefully.
Yes, you squeeze gingerly. So all the different observing programs and what an FFT is, if you want to look about Fourier transforms and such. And then what actually is a sensor, how they're connecting all these things together with machine learning and AI. And what's a petabyte? I had heard of megabytes, but what's a petabyte? Oh, that's old stuff. Nowadays they're exabytes, which are thousands of petabytes, because there is actually a storage facility in the US owned by the NSA that has exabytes of storage for all that stuff that they're not listening into. And then if you want to know, what is that photoelectric effect that guy Einstein came up with? And you see at the end, like, subscribe, notify, share, and Patreon. I got the little emojis and icons down there. So people can watch it. If they like it, great. Come back for more. If you follow Broward Astronomy on Facebook, because I've got my own Facebook page, but if you follow Broward Astronomy on Facebook, when I post the videos, you can get notifications. Okay. Comments, questions?
Looks like there's a whole field available for people who want to invent different kinds of sensors.
Yes, there is. And in fact, the way we used to measure gyroscopic actions and accelerometry is using little tiny, very high-speed moving wheels on very, very good bearings. And we had little magnets on board the spinning things, and you would spin them up to speed, and then they would run at that speed for a certain amount of time before they would eventually start to slow down, and then you would spin them up again. And once it's spinning at a certain speed and you measure the angle of the magnetic field change, it'll only go so far. It'll become what is known as saturated. So, for example, the Hubble Space Telescope has gyroscopes. When it wants to tilt too far over or wants to track an object for too long and it goes too far, you hit the threshold limit of the gyroscopes. And what you have to do is recoil the gyroscope, spin it back down, spin it up the other direction until it gets back to stable speed. And then you use your rocket thrusters or your momentum wheels to pull the telescope back up to where you want it. So now you can start from there down. I think it's akin to a puck that you might use with a computer has a limited square area that you move in, and your entire display area, XY coordinates, fit within that scale area. That's a puck. But a mouse is different. A mouse, the pointer moves relative to the motion of the mouse. So you move the mouse, and if that's not far enough into the corner, you pick the mouse up, you do what is known as skate it, and then you put the mouse back down, and now you can move the mouse some more. Mechanical accelerometers and gyroscopes, they have to work like a mouse versus a puck. Whereas a MEMS chip, they can't get saturated. They will continue to produce a voltage out regardless of how far you tilt them over. So when they found out that, MEMS chips, yeah, those are good. First of all, we can crank them out by the thousands, so they're really, really cheap. An individual MEMS chip giving you XYZ is about 5 cents cost. And then you put it on a circuit board that's 50 cents. And then you do that for 10 degrees of motion. So you have 3 accelerometers, 3 gyroscopes, 3 magnetometers, and 1 barometric pressure sensor. So 3, 6, 9, 10 degrees of freedom, all in one little circuit board, a little bit bigger than a postage stamp, that's maybe $20.
Isn't the Hubble Space Telescope suffering from gyroscope failure?
Yes, because think back when it was put in space. It's using mechanical gyroscopes. It's not using MEMS chips.
Well, that was what I was just going to ask you. I mean, it would seem that the MEMS chip would last wouldn't have the problem of spinning around and wearing up something. Yeah. But is it reliable enough? Will MEMS chips play? I'm sorry, you're saying MEMS, MEMZ, what is it again? What does it stand for?
MEMS, Micro-Electro-Mechanical System, MEMS.
Okay, so I'm sorry, I'm embarrassed. I didn't. So will they replace all the gyroscopes that are used for space flight and space travel and satellites?
Yes, they're already doing that for existing satellites, for newer generations of satellites. They won't do it on the Hubble because MEMS chips do not behave like moving gyroscopes. If they do a refurbishment, they will most likely put in moving gyroscopes with better bearings, because there are software algorithms that are in the observing procedures of the Hubble that work based upon rotating gyroscopes. And if all of a sudden you replace it with MEMS chips that don't rotate, the algorithms are going to be wrong. So it's much easier and more reliable to just keep with the well-known, well-understood moving gyroscopes than it is to not only replace the mechanics of the gyroscopes, and all the electronics that feed them and all the sensors that come off of them, but also all these software algorithms for using them.
Well, sure, and replace the chips with 8088 chips or whatever.
Yeah.
Wow. So now this has been a brilliant talk tonight. Now I just need to work on an ion traps, mem regulating space vehicles. So that's great. Thank you.
Well, if you really get interested in it and you want to find out more, there are places I can send you to, deep rabbit holes where you won't come up for days.
Well, of all things, the reason I was interested anyway is this is going to really date me, but Ed Haynes once said to me, when microprocessors reach 100 megahertz, that's a really key threshold, because then you can run fast Fourier transforms real time for radio.
Yep.
So imagine microprocessors didn't go at 100 megahertz at one time.
Yeah. And in fact, some of the processors we used on those computers didn't get to 100 megahertz. So you were at Scientific Atlanta talking to Ed. Meanwhile, I was at Telematics working on computers that were running at 80 megahertz or 60 megahertz. So nowadays, I can go buy myself for $15 a Raspberry Pi 02W that has a quad-core 1.5 gigahertz processor that has a half a gigabyte of RAM. So yes, I can attach my software-defined radio that will receive in frequency ranges from 0 hertz up to 1.2 gigahertz continuous. So yeah, things have changed. As the saying goes, we live in amazing times, and we're just getting started in the quantum realm. So 50 years from now, it'll be awesome.
I have a question when you go off a recording.
Okay. Any questions while we're still recording? Hearing none, we'll stop recording.